We're going to talk about nuclear chemistry in this section. This is usually a really interesting module because a lot of people don't know very much about nuclear chemistry. All they've heard is like Chernobyl and 3 Mile Island and what are nuclear plants. There's one really close by to Chattanooga, and what does that mean? So those are the kinds of general ideas people have, but they don't really understand what is nuclear chemistry and what it does. Plus, through on top of that, we've got all the movies out there. We've got the Marvel movies where people get hit by radioactivity and they develop superpowers, you know? So what does radioactivity mean? What does it do? Where does it come from? Those are the kinds of questions we're looking at in this section. So before we move on, we're going to look at isotopes. And this was in General Chemistry 1, really close to the beginning, probably the second week of you doing General Chemistry. We learned about isotopes. So isotopes are when you have the same number right here of protons. So all these have 6 protons, and we have the same number of protons. That means you're the same element. So it's the same element, but with different numbers of neutrons and protons. Since you can't really change the number of protons, what it is different number of neutrons. This top number is when you add your neutrons and protons together. And then if you'll notice right down here, this is what you get when you subtract your neutrons plus protons from your protons, and that tells you how many neutrons you have. So you can tell we have different numbers of neutrons for these isotopes. So molecules or elements have all different amounts of isotopes. Some elements have a lot of isotopes and some don't have very many at all. And you have isotopes that have different abundances. For carbon, this is an interesting example because carbon-12, 99% of it is that carbon. But then 1% of it is actually carbon-13, and then 0.0001% of it is carbon-14. And all of these different forms of carbon are actually useful, and it's really good that we have all those different percentages. So of the 3 types of isotopes, there's only one that's radioactive, and it's this one right here. So this is our radioactive carbon. The other carbons aren't radioactive at all. So if you look at the difference, notice we do have a lot of neutrons in there. So just with this one single example, what you might think is that maybe radioactivity has to do with instability related to maybe too many neutrons. And if you're thinking that, you're on the right path. That is one way that you can get, and you can end up with radioactivity. Let's go over and look at a nucleus. It's not really a nucleus, obviously. We're going to look at how a nucleus stays together. So a nucleus essentially it has a little bit of a problem because it's only made up of positively charged protons and then neutral neutrons. Well, the positive protons, these all have to be in a very, very close space. Like they have to be really tightly together. And so now we have all these positive charges that are going to be repelling each other, and yet they're supposed to stay together in a nucleus. The neutrons help because the neutrons kind of can give some spacing to those protons. But what holds an atom together is actually called the strong nuclear force. It's very, very strong, but a very short distance. It only lasts about across the diameter of the atom. So especially with smaller molecules, you could see that the nuclear force will help hold all of these together, right? And I'm just making this up how this is joined together, but they help hold each other together. So if you can imagine this being like 6 times larger, that's a lot of things to hold together with just these short little distance forces pulling on them. Now that is very strong, very, very strong. I don't want to underemphasize that. These are very strong forces that are holding the nucleus together. But once you get to a certain point and you're a certain size, it's just hard for those little tiny short distances to hold an entire nucleus together. So that is actually an issue. So one issue is just way too large of a nucleus is going to have some instability. Another issue is that if you have too many protons too close, essentially what that means is that your proton to neutron ratio is really high. It's not, what the atom wants it to be. That can lead to instability. And actually also the reverse. if your neutron to proton ratio is high. So if your neutrons are a little off from your protons. So then the question comes out to being, well, what is the right ratio? What is the right size for a nucleus for stability? And what allows it to exist, but it's unstable? And what does unstable really mean? All right, let's look at this picture right here. And I've got a few things in here. So what this picture is telling us is where are the stable isotopes. So the blue is the stable isotopes. These are the non-radioactive, the ones whose nucleuses are happy. Then we have the radioactive, so they exist. It's not so unstable it won't exist, but they're not super happy. They've got some stability issues, and they will start throwing out either neutrons or protons, or they'll convert things, they'll throw out energy. They're going to throw things out of the nucleus to try to make it more stable. So you can see the green is a much broader color. So if we go back to that neutron to proton ratio, this right here is the number of protons. So for neon, this is what makes neon neon. It's got 10 protons. That's great. This is the number of neutrons. So 2010 neon has 10 protons, and it has 10 neutrons, because don't forget you add the two together to get the top number. And notice that it's on this line. And so what this line is doing is it's showing us where your neutron to proton ratio is exactly the same. You'll notice when we're little, it's totally fine and we're happy. But as you get broader and further out, do you see how we, like right here, we're in the boundary even of existing. And then right here, it doesn't even exist over that way. So the larger the atom, the more neutrons are needed in general. The smaller atoms can kind of deal with it, you know, but the larger atoms, they need more neutrons. And then as you head up in this direction here, there's a point at which, let me actually go right here, this element, we go all the way down. It's going to match up with, I believe it's 82. This is lead. So lead right here, 82 lead, is the last element, so it's the last number of protons that are stable, period, that have at least one isotope that's not radioactive. So everything after lead, every isotope is radioactive. So basically, more protons than 82 is going to be unstable. Here's the other thing though. And I love this about radiochemistry people and nuclear people, is they come up with great names for things like magic numbers. And so what we have found is that there are magic numbers of stability for the nucleus. And it happens when you have 2, 8, 20, 28, 50, 52, 82, or 126. Those numbers of protons will create quite a bit of stability. You'll still have isotopes that are radioactive. We're not saying you won't, but you get a wide range, basically, of isotopes that can at least exist. But notice this right here. This is 1050, so it's just this example right here, and this is at the lowest point of it. This one has 10 stable nuclei, and then you can see this big long swath right there. And then it also it has more that aren't stable too. But then if you look at indium and Sb, so these are like right beside it, but those only have 2 each. So we have these regions of stability. If you want to go really deep into chemistry, you could Google this and find out reasons why we think that these have magic numbers of stability and why it is what it is. But suffice it to say that when our nucleus has, when it doesn't have enough neutrons, when it has more protons than 82, and when it's not one of these magic numbers, then we're going to have instability, and that's going to lead to radioactivity.